Hey class, Physics 30, it's Mr. Hofstad here with Lesson 8. I'm not going to go through the examples as you can find those on Mr. Holloway's, but I will walk through these notes with you and try to explain them in a little bit different words than just from the notes. So today we're looking at one very specific model of one very specific atom, but it's really kind of the bridge between classical and quantum theory. Right, so we're getting into this idea of quantum, right, and that comes from this understanding of quantized, or these specific kind of rings or locations, right? So everything is grouped into nice, neat, wow, I really need to get a tablet. Well, you can write quantized here if you want. Apparently, I can't do it with my trackpad. All right. So this idea of quantum theory is all about keeping things quantized. So what that really means is that we have these electrons orbiting in specific tracks, right? And these discrete rings, or these discrete orbits where they'll actually exist, with none of them orbiting anywhere in between here. So an analogy I like to think of is these electrons are like athletes in the Olympics or on a high school track team running around a track, and they have to stay in their correct lanes, right? They can't run in between two lanes or they'll collide with another athlete, right? We need to keep everything organized and in their separate lanes. This is true for electrons in this model. They can only be located at certain radii, never in between. They need to remain at a constant allowed orbit. So if they are within this orbit, they're not going to be emitting any EMR despite their acceleration. And this acceleration is, of course, centripetal acceleration. They're not actually changing their velocity, they're just changing their direction as they undergo uniform circular motion. So within this model, we have this lowest orbit or lowest energy state, which we call our ground state. So lowest energy state, you'll often heard as unexcited or ground state. So if any of those words come up in a problem, you know that you're working with this lowest energy level, right? So lowest in this case means most negative, because all of our energy levels are negative except for this highest level, our upper level, where the electron is now actually free, right? So we call that our zero energy level, and everything orbiting lower than that, right? So if we were to draw this n equals infinity around this one up here, it would be somewhere outside of this, right? And as soon as the electron is removed or has more energy than that, it's going to escape, right? We have an electron leaving our atom, breaking that electric force between the proton and the electron. And that's what we call ionizing, jumping a bit ahead in the notes here. When it goes beyond this n equals infinity, it's leaving the atom, right? It's escaping its orbit, and it has some kinetic energy, depending on its velocity. All right, each of these allowed orbits, or each of these levels or tracks, however you want to think about them, has a different required energy level. So the electron must have the exact energy, right? Electron needs to have the exact energy in order to be on that energy level, or that radii of this orbit. right? It can't exist anywhere in between those orbits. It needs to be exactly this number here, or this number, right? We need to have exactly that much energy. The energy levels that Bohr calculated are all shown here. Don't worry about memorizing that. That, of course, would be given in a question. So the important thing is that you need to have exactly the amount shown. The minimum energy, right, would be its ionization energy. The minimum energy to remove our electron from any sort of electric pull to the proton would be our ionization energy. And now we have a free electron shot off into space. And we're left with a lonely old proton that would be a positive ion. All right. Well, that's kind of where this idea of ionization comes from, right? We're left with a proton by itself, positive ion, and an electron by itself, a negative ion. Okay, so this idea of orbits lends itself nicely to kind of a review of our physics 30 concept of uniform circular motion. So we have an electron orbiting at a constant radii around its proton. Instead of this being a gravitational force like we would have with a moon orbiting the Earth or the Earth orbiting the Sun, we're not being pulled in with a gravitational force in this case, but instead we have an electric force between the negative electron and the positive proton holding it in its orbit. And with uniform circular motion, our net force is almost always the result of just one force, whether that's tension on a string or gravity. In this case, we're working with the electric force between our electron and proton. So we can break up Newton's second law, principle of physics 1, where the net force is equal to that mass of this electron times its centripetal acceleration, right? And the net force would be all due to this electric force. There might be a little bit due to gravitational, but it'll be so small compared to the electric force that we can just completely forget about it. And from our formula sheet, we have the electric force is equal to our K times the charge of both the proton, K1, and the electron, or Q2. The order doesn't really matter there, divided by the radius between the proton and the electron's orbit. And that would be equal to the mass times our velocity of this orbit, this uniform velocity, changing direction but not magnitude, squared, divided by, again, the same radius between the proton and the electron. Just remember that our K is Coulomb's constant, and that's given on our formula sheet as 8.99 times 10 to the 9 Coulomb. Okay, and with a little bit of rearranging and a little bit of canceling, we end up, so this is an alternative way to write it if we're just working with one charge. I don't even know why that's in here. I don't like that one. Right, because the charge of the electron and the proton will be different. So you'll have to multiply each of their charges. I would cross this one out and rely on this one. Okay, this first example, see Mr. Holloway's video. Wow, because I don't want to put you through me trying to write using my trackpad. You get the idea. The other Mr. H. This is just painful. All right, moving on to the next page. Hopefully you can follow along with this idea, right? We're all just relating back to this formula. We're given a radius. We know the charge of the electron and the proton from our formula sheet, so the rest should be nice and simple algebra. Okay, Bohr came up with that idea of quantized orbits, right? And that allowed him to think about these emitted photons, right? Or absorbed photons. So this was all in an attempt to explain the different absorption and emission spectrums of heated gases. And as you can see, if an electron is starting at this upper energy level and dropping down to a lower energy level, what this would look like would be it's starting somewhere like n equals 4 and then dropping down either to n equals 2 or its ground state, right? But we're just having this electron moving from one orbit to a lower orbit with a more negative or a lower energy. Because, right, somewhere way up here we have our n equals infinity, where we're actually at 0. So we got to get used to working with all negative numbers. And a more negative number means that we're decreasing the energy. So when we're going from this upper limit down, we're going to have a decrease in energy, right? A loss in energy, but we can never truly create or destroy energy. So instead we are releasing or emitting a photon. This is the light that we see. Conversely, if a photon hits an electron with the exact amount of energy required to raise it to a higher energy level, we're going to then have it shift to a higher orbit. And we'll have this electron and this atom increase its energy. So the photon is absorbed. This is really key. We need to have the exact amount of energy in the photon as the energy required to make that jump. So when it hits and it has the exact energy, we're raising this electron up to a further away orbit, right? This would be like going from n equals 1 to n equals 2 or something like that, right? It's going upwards. We have an increase in energy, and as a result, that photon is no more. This would be our absorption spectrum. This would be an emission. This would be an absorption spectrum. Right, just like we talked about last video with these bright lines and these dark lines in different atomic spectra. When you're shining white light through a gas in low pressure, like a neon sign, right, we're either going to have bright emitted lines, that's a result of this jump, or another way to say it is a quantum leap, right? Or we can have these dark lines, right? That would be passing white light through, right? All of these photons would be absorbed, right, as they increase electrons. So this one would be when we run a current through that neon sign. We're going to get into that a bit later on, but we'll have photons emitted. So, right, we know we have this law of conservation of energy. The energy gained or lost by the electron, which is very important, our transition energy, right? The change in energy of the electron as it transitions from one orbit to another must be equal to the photon, right? So this is our new formula, and it is not on our formula sheet, but we can keep this one, right, without memorizing. just by thinking about conservation of energy. So the change from that final minus initial, right? So upper minus lower for this one, right? If we're going from here to here, it would be the other way, and we're going to have an increase in energy, right? It depends on emitting or absorbing photons. Okay, again, see Mr. Holloway's videos for a nice walkthrough on these questions. And I will continue with the last page of notes for our 9th lesson. So again, putting it into context, if you ran a current through this low pressure hydrogen gas, right, it would emit these bright lines, right? So you're going to have infrared with all of the higher energy, infrared would be lower energy, bigger wavelength, smaller frequency, electromagnetic radiation, and then UV would be higher energy, shorter wavelength, higher frequency. But we have these visible light bands that we would see, and this is where Bohr's explanation, right, could be tied into an experiment that they had here, that they were trying to come up with a theory to prove. So the first question they were trying, or Bohr was trying to answer, was why does this excited low pressure hydrogen gas emit only certain or discrete frequencies of EMR? So why is it quantized, right? Why aren't we getting any of this yellow and orange or this purple? Why are we only getting these discrete bands? So first of all, the high voltage current created within the cathode ray tube. So we're going to be shooting electrons from our cathode to our anode. As those electrons are being shot through this gas, they're going to collide with a hydrogen atom. So this is similar to a photon colliding with a hydrogen atom, like we looked at last page here, where we have a photon carrying energy, transferring that energy to a hydrogen atom. But here, even more concretely, we have electrons colliding with them and transferring energy, right? Electrons have mass. They obviously can transfer energy from them as they're moving across to these hydrogen atoms. So when they do collide with the hydrogen atoms, they're going to give them some of their energy. They're going to excite them into these higher energy levels, right? So instead of having photons with these collisions, we now are getting the electrons from cathode to anode that are creating this excitement, right? This energy transfer. So since those electrons or atoms, right, we can kind of think about it either as an atom or an electron here with hydrogen, because there's only one electron per atom. It's a nice simplified, easy to work with case. Since the energy levels are unstable, eventually this atom will drop to a lower energy level. So that electrons collided with our atom, right, the electron orbiting the atom, and raised it up to a higher energy level. And from this higher energy level, this electron is orbiting for a short time, but it really doesn't want to stick around there too long, right? The higher energy level it's at, the more unstable it is. This is a little bit beyond the scope of Physics 30. All you really need to know is that electrons want to be at this ground state, right? That's kind of their favorite state of being. This is when they're happiest and most chill. So when it gets excited, brought all the way up to one of these energy levels, it's going to try to drop down, right? Sometimes it'll just drop down 1 energy level, sometimes it'll drop down like 3, sometimes it'll make this big 5 energy level jump. Again, you don't really need to know why they're making different jumps at this level of physics, but just understand they're always trying to go back to this ground state. So these atoms or these electrons, right, you can think about it either way here because we're working with hydrogen. Those electrons within the atom will drop to a lower energy level when they drop levels, right, as we are moving from this 5th orbital down to our 2nd orbital. We are having a decrease. We're going more negative. We're having a decrease in energy. So it's losing energy, and we need to conserve energy, so we will emit a photon, right? That energy loss from it traveling from this orbital, this energy level downwards, needs to go somewhere, and that's where we're getting photons from. So Bohr was able to show that each bright line of the emission spectrum had its own unique energy drop. So all of the visible light spectrum just happens to be a drop from one of these 3rd, 4th, 5th, or 6th energy levels down to the 2nd, right? Of course, the electron often will drop all the way down to the ground level, but that's such a big drop. Going from really any of these back down to ground state, we have such a dramatic jump, so much energy loss, that the photon that we emit would be somewhere in our UV range, right? So these energy drops to ground state are so drastic that we're not able to see them, right? We'll only be able to detect them with some ultraviolet detector. But do understand that all of these other drops down to the 2nd energy level will result in photons emitted with these very discrete wavelengths, energy levels, right? And that's what's creating these bright bands in this light emitted from excited hydrogen atoms, right? This emission spectrum. All right, hopefully that's making a little bit of sense, right? You can see that if it's going just from 5 to 6, right, we're having a pretty small energy drop. So this would be infrared, right? Anything going down to our ground state would be UV. Anything going to this 2nd orbital state, right, n equals 2, would be our visible. Okay, so it can make any of these jumps. We could even go from 2nd to, from 5th to 3rd. I don't know if there is an example of that one shown. Yeah, apparently that one falls outside of, it's kind of in between. But you'll see, right, infrared are the lowest energy, so we have the smallest gap. I think that might actually, going from 5 to 3, would probably fall under infrared. Right? Anything going to 3, anything going to 4, or anything going to 5 would produce these lower energy photons, like infrared radiation. All right, Bohr was also able to explain why gas absorption, right, requires the same frequency of EMR that it emits. That makes sense. We're just going the opposite way now. We're going from this 2nd state up to either the 3rd, 4th, or 5th, right? And the photon that enables it to make that jump will be absorbed, and we're going to get that dark line in our absorption spectrum as a result. So to illustrate, Bohr knew that when a hydrogen atom dropped from 2 to 4, or 4 to 2, it emits green photon with this very specific energy and wavelength. So in order to raise the hydrogen from 2 to 4, going in the opposite direction, we're going from 2 now up to 4, we would require this same energy level photon, right? To collide with that electron and raise its energy, right? Excite it to that exact energy level. So hopefully that's a nice obvious connection, right? We're working with quantized orbitals, so it will always take the exact amount of energy to either absorb or emit an electron, right? We are still working with the same quanta or the same discrete amount of energy. Only photon that can actually do this is with the exact energy would be the same photon that it would otherwise emit, right? That'll be true for every single wavelength photon absorbed or emitted by the hydrogen. So keep in mind that this whole lesson is all about hydrogen. It's therefore quite a simplified model, right? So Bohr's model couldn't explain absorption spectrum for anything other than hydrogen, right? Hydrogen only has one electron. This is a great, easy to work with introduction, but working with more complicated elements, right? Atoms that have multiple electrons, we're going to have to come up with a new model, right? We couldn't explain the spectra for more complex atoms. Right, as soon as we had multiple electrons, right, things start interacting with each other in weird ways, and that's what we're going to get to into with our next lesson, just briefly. Most of that is more university level chemistry and physics. So he didn't understand why, right? He could interpret the data that they were only in certain orbits, but he couldn't explain why. He also didn't understand fully why the orbiting electrons didn't emit EMR, right? Because they still do, as they're orbiting, have this centripetal acceleration. So going back to before the whole quarantine, we were talking about eventually you'd have the electron spiral inwards and collide with the proton, and that would take like nanoseconds to occur, and we shouldn't have any atoms with their orbiting electrons, right? They should all be emitting EMR for a split second and then collapsing in on themselves. So he still, with this model, couldn't explain why they didn't emit EMR, even though they were accelerating. And finally, why some spectral lines were brighter than others. So in order to explain all these, we need to kind of dip our toes into quantum mechanics and the quantum model of the electron. We won't get too deep, I promise. That's for you to explore on your own or in university, because it is exciting stuff, and learning more about how the world works is always a noble and worthwhile task. All right, talk to you guys later. Thanks for listening.